Welcome to today's Deep Dives, everyone, where we'll be diving into the world of inorganic chemistry.
Yeah, getting down to the nitty-gritty,
I like it.
how those elements behave.
And we've got our hands on some university-level lecture notes this time on atoms and periodic trends.
Excellent.
Yeah,
That's fun stuff.
we're taking those dense textbook pages and we're going to,
Yeah, we're going to decode
them exactly.
We're going to make it make sense.
Yes, and you know what we're starting with? The periodic table.
Of course, the centerpiece of chemistry.
It's like this massive chemistry cheat sheet.
It is.
But
It can be a little intimidating.
it can be a little intimidating when you first look at it.
All those numbers and symbols.
Oh, I know.
Easy to get lost.
So walk us through it.
Okay.
What's the deal with the periodic tables organization?
So the beauty of the periodic table is that it's not random at all. The position of each element reveals these patterns in its properties, how it behaves, who it bonds with, the whole shebang.
So it's like a giant puzzle
Yeah.
where each piece fits perfectly.
You got it.
Okay.
Instead of memorizing this, jumble of facts, you can actually predict an element's personality just by its location.
What?
Yeah, we can tell if it's going to be a loner or a social butterfly, chemically speaking, just by where it hangs out on the table.
Okay, now that's what I call intriguing.
Yeah.
So for example, can we really figure out an element's electron configuration just by finding it on the periodic table?
Absolutely, you bet.
Wow.
It's like being a detective, using those clues to build a profile.
I love that.
Let's take argon, or R as its friends call it.
Okay.
Find it on the periodic table over there, chilling with the noble gases in group 18.
Got it. Third row down all the way on the right side.
Perfect.
Okay, now here's the trick.
Okay.
The group number is key to cracking the electron configuration code.
Oh, since argon is in group 18, that means it has a full outer shell of 8 electrons, right?
Right, the noble gases are all about that stable light.
Yes.
With their full outer shells.
Precisely.
Okay.
So working backwards, we fill up those electron shells.
Okay.
Argon's in the third period, so his electron configuration starts with 1s2, 2s2, 2p6.
Okay, keeping up.
That gets us to 10 electrons,
Okay.
then 3s2, 3p6.
Oh my good.
Boom, a full outer shell, just like we predicted.
That's like magic.
It's like chemistry magic.
So just by knowing argon's address on the periodic table,
Yes.
we can decode its electron configuration.
Exactly.
That's way cooler than I ever thought.
And that electron configuration is key to understanding how argon behaves. It's like having the instruction manual.
You're blowing my mind.
I know, right?
So we've got this amazing organizational tool, the periodic table.
That's our map.
It's like a map to this entire universe of elements.
And we're just getting started.
Ooh, I like where this is going.
Now that we know how to read the map, let's zoom in on some specific atomic properties.
Okay.
Things are about to get really interesting.
Okay, so we've decoded the periodic table and figured out how to read an element's electron configuration just by its location.
Yeah!
That's some serious chemistry detective work.
It is, and that electron configuration is going to tell us even more about an element.
Like what? Spill the tea?
Well, you know how some atoms are bigger than others? Like some are these fluffy clouds,
Yeah.
and others are more like tightly wound balls of yarn.
Okay, I can picture that.
Yeah.
So we're talking atomic radii now, right?
You got it. And it turns out size really does matter in the world of chemistry.
Okay.
Atomic radii influences how an element behaves, who it bonds with. It's high school all over again,
Whoa.
but at an atomic level.
Okay. I am so here for the chemistry drama.
Right.
So how do we know which atoms are the popular kids and which ones are stuck at the lunch table by themselves?
Well, think of it this way. As you move down a group on the periodic table, atoms generally get bigger. More electron shells, more fluffiness.
Makes sense. More layers, like adding another coat of paint.
Exactly. But here's where things get a little counterintuitive.
Okay.
As you move across a period from left to right, the atoms actually get smaller.
Wait, really?
Yeah.
That doesn't seem fair. More protons. More electrons. Shouldn't they be expanding like a balloon?
You'd think so, right? But those inner electrons, they're not the best at sharing the spotlight.
Oh, no.
They don't do a great job of shielding the outer electrons from the positive pull of the nucleus.
So it's like those inner electrons are hogging all the attention from the nucleus?
Exactly. And as you add more protons and electrons across a period, that pull gets stronger.
Okay.
And the whole atom actually contracts.
Really?
Yeah, it's like someone let the air out of that balloon.
Wow. Okay, so size isn't always about how much stuff an atom has.
Right.
It's also about how tightly that stuff is held together.
Now you're getting it, and just when you think you've got it all figured out,
Uh-oh.
The periodic table throws you a curveball called the lanthanoid contraction.
The what?
Lanthanoid contraction.
Okay, hit me with it.
Picture this. You're cruising down the 6th period of the periodic table.
Okay.
Elements getting bigger, just as we'd expect.
Okay.
But then after the lanthanoids, those elements hanging out at the bottom,
Yeah.
the atoms are suddenly smaller than they should be.
It's like they hit a cosmic shrink ray. What's going on there?
Blame it on those lanthanoids.
Okay.
They're kind of notorious for this.
Okay.
Remember how I said inner electrons can be bad at shielding?
Oh, yeah, those attention-hogging inner electrons.
Well, the 4f electrons, which are being filled in the lanthanoids, are the absolute worst offenders.
Oh, no.
They do such a poor job of shielding that the outer electrons get pulled in super tight,
Wow.
making the atoms unexpectedly compact.
So even though those atoms have way more electrons than the ones above them,
Yeah.
they're practically the same size.
Pretty much take molybdenum, Mo, and tungsten, for example.
Oh.
Tungsten is 2 periods down from molybdenum, meaning it has a whole extra shell of electrons.
So like adding an extra layer to a cake, you'd think it'd be way bigger, right?
You'd think so.
Yeah.
But in reality, tungsten's radius is only a tiny bit bigger than molybdenum's.
Get out of here.
We're talking a difference you'd need a superpowered microscope to see.
That's wild.
Yeah.
So those 4f electrons are seriously strong-arming those outer electrons.
You could say that the lanthanoid contraction is a prime example of how those inner electrons exert their influence.
Okay, my mind is officially blown.
Good.
Atoms are way more complex and sneaky than I ever realized.
They are sneaky little things.
But this all ties back to those electron configurations, doesn't it?
Absolutely. The number and arrangement of electrons dictate not only an atom's size,
Okay.
but also its energy.
Energy. Like, are we about to talk about atoms powering entire cities? Because I'm here for it.
Maybe not cities, but how about powering chemical reactions?
Okay, powering chemical reactions, that sounds more my speed.
Yeah.
But seriously, what does energy have to do with atoms?
Well, electrons aren't just hanging out in their shells, doing nothing. They have energy. And that energy determines how an atom interacts with other atoms, whether it's eager to make friends or perfectly content on its own.
So it's all about those electrons. I'm sensing a theme here.
Exactly. And we can actually measure an atom's enthusiasm for gaining or losing electrons.
Oh.
We use 2 key concepts, ionization energy and electron affinity.
Ooh, fancy terms. Break it down for me.
Okay, so ionization energy is basically how much energy it takes to pry an electron away from an atom.
Kind of like convincing me to share my pizza. It depends on how hungry I am, right?
Exactly. And just like with pizza, some atoms are way more attached to their electrons than others.
Okay.
The higher the ionization energy, the more attached that electron is, the more energy it takes to steal it away.
So high ionization energy means an atom is basically an electron hoarder.
You got it. Now, on the flip side, we have electron affinity. This measures an atom's eagerness to gain an electron.
So are we talking about atoms who are like, come on over, electrons, we've got plenty of space?
That's a great way to put it. The higher the electron affinity, the more an atom wants that extra electron.
Okay, I'm starting to see the difference. One is about holding on to what you've got.
Hmm?
The other's about welcoming newcomers.
Exactly. And as you might have guessed, these properties tie back to our good friend, the periodic table.
Of course, there's always a method to the periodic table's madness. What are the trends we need to know?
Well, ionization energy generally increases as you move across a period. Those smaller atoms, they hold their electrons tighter, remember, and it decreases as you go down a group. Bigger atoms are a bit more relaxed about sharing the electron wealth.
Ah, so those bigger atoms with electrons far away from the nucleus, they're like, you want one, take it, be free.
Exactly.
Yeah.
Now, here's a fun fact. Each successive ionization requires more and more energy.
Wait, what does that mean?
Imagine trying to take a French fry from my plate. Absolutely not happening.
Okay.
First ionization energy is like asking politely, maybe I'll give you one. But trying to take a second, forget it. That's going to require way more energy if you catch my drift.
Okay, so trying to steal a second electron is like trying to snatch a French fry from your plate, not happening. I can definitely relate to those fiercely guarded electrons. Can we see this play out with actual elements?
Absolutely. Let's look at lithium. Its first ionization energy is relatively low. It's pretty chill about losing one electron to become a positively charged ion. But try to take away a second, and it's a whole different story.
Yeah.
The second ionization energy for lithium is huge because now you're trying to steal an electron from a stable inner shell. That's like prying away the last fry.
Makes sense. Those inner electrons are like, nope, we're good here. Nice and close to the nucleus, not going anywhere.
Exactly. And this difference in ionization energies tells us a lot about an element's preferred charge when it forms ions, which brings us to...
Bonding. We've got to talk about how atoms connect with each other.
Right. It's like chemistry matchmaking, but instead of compatibility quizzes, we've got ionization energies and electron affinities.
So an atom's eagerness to gain or lose electrons totally affects how it bonds with others, right? It's all about finding that perfect chemical match.
You got it. Think of chemical bonds like different levels of commitment between atoms. A single bond is like a casual handshake. A double bond is a hug. And a triple bond, that's a full-on commitment.
I love this. So some atoms are more into those casual handshakes while others are ready to jump right into a long-term partnership. It all depends on their electron baggage, right?
You said it. And the strength of these bonds, or how much energy it takes to break them apart, depends on the atoms involved and where they hang out on the periodic table. We call this bond enthalpy.
Bond enthalpy, another term for my growing chemistry glossary.
Add it to the list. And remember how we talked about smaller atoms holding onto their electrons tighter?
Yeah.
Well, that translates to stronger bonds. Think of it like two people holding on tight during a trust fall. The closer they are, the stronger their grip.
So those smaller atoms can really pack a punch when it comes to bonding.
Absolutely. And some atoms have a clear preference for a specific type of bond. Take oxygen, for example. It's all about those double bonds forming O2, the very air we breathe. But its neighbor down below, sulfur, is much more chill. It prefers single bonds forming rings or chains.
Wait, so even though they're in the same group, oxygen and sulfur have different bonding styles. It's like those twins who have totally different personalities.
Exactly. It all comes down to bond enthalpy, that energetic push and pull. Oxygen's double bond is way stronger than its single bond, so it's much more energetically favorable for it to double up. But for sulfur, the difference isn't as dramatic, so it's cool with either one.
So thanks to oxygen's strong double bond preference, we get to breathe easy. That's pretty amazing.
It is. And this is just one example of how those tiny atomic tendencies we've been talking about actually shape the world around us.
Okay, I need a minute to process all of this. We've gone from decoding the periodic table to understanding electron configurations, ionization energies, and now how all of that influences chemical bonding.
We've covered a lot of ground.
We have.
But that's the beauty of chemistry. It all connects.
It's like a giant web, and every atom is a tiny but essential part of it.
Exactly.
Well, this deep dive has been incredible. Huge thanks to you for guiding us through this fascinating world of inorganic chemistry.
My pleasure. It's been fun.
And to our awesome listeners, we hope you've enjoyed this whirlwind tour of atoms, electrons, and the amazing dance of chemical bonding. Who knew something as small as an atom could be so complex and so essential to understanding everything around us? Keep those brains buzzing, and we'll catch you in our next deep dive.